Thank you. Okay, so hi everyone, I'm Roberto. I work for CIRAD, which is the French Agricultural Research Center for International Development. I think so. And it's an institute who works for the agricultural development of southern and tropical countries mainly. So I'm part of a joint research unit, TETIS, which is based in Montpellier. So today we will talk about how to extract multi-layer networks from satellite images time series. So first of all, what are satellite images time series? I don't know if you are familiar with this data type. I guess it's not the right community maybe for this kind of things, but it's rather intuitive. It's just exactly what the name says. It's a time series of satellite images, so taken on the same area at different subsequent periods with fixed frequency and resolution. So these time series are gaining increasing success. They are used in a lot of domains for ecology, culture, mobility, health, and a lot of other tasks. You can imagine an infinite number of applications for that. And if we just focus on agricultural monitoring, so there are still a lot of sub-tasks like land use, land cover maps, change detection, damage assessment. So it's a really popular data type for a lot of tasks. What's the problem? The context is that most approaches are supervised approaches, are machine learning based ones, which are data hungry, so you need to collect data because the level of data is scarcely available. When I say collect data, I mean you actually have to go on the field. So if the field is in Africa, you have to go in Africa, do your tour of the area and label all the zones and say this is a cropland, this is a natural forest, this is urban assessment, whatever. So collecting data is really, it's an expensive in time and money activity. So what is good about satellite images time series these days is that in the last years there have been a lot of new satellites, new missions that provide data which is publicly available. One of these missions is the Copernicus program, which is led by the European Space Agency, ESA. And for example, we have this Sentinel-2 satellite. It provides optical satellite images at high resolution, so 10-meter resolutions, meaning each pixel is 10 meters on the ground. And high temporal revisit, so we have a new image every 5 days. So this is open data, everybody can access to that, it's free of charge. And satellites with even higher resolution than this exist, like Spot 6, Spot 7, but you have to pay for that. You can have resolutions up to 1.5 meters, but you have to pay for that. This is free, so in research we tend to use this, at least for as regards time series. Because you also can have a good revisit period, so an image every 5 days, you can imagine, very rich time series during a year. So why we would extract a multi-layer network from a satellite image time series? Yes, first of all, because then you can represent the satellite images time series as a single interconnected object that can integrate different informations, different relations, and for example, spectral, textual, and contextual information in the same object. And then, by consequence, you can imagine to adapt network analysis techniques to this kind of data object. So, in order to devise some unsupervised, for example, remote sensing methods, rather than the supervised machine learning ones that I use these days. So, all the images and all the experiments presented in this presentation are referred to case studies in Burkina Faso, so in the West Africa, and more precisely on the Cumbia zone, which is an agricultural zone in the western part of Burkina Faso, which is a really challenging zone due to the fragmented landscape. There are a lot of small agricultural plots with confused borders, great variety. So for this kind of task, it's a really challenging zone. And it's a site that we monitor at CIRAD since 2014, and Sadly, this is the first year where we could not go there to do our field campaign because we were refused the authorization for security reasons. This is very sad, but okay. And we, for this work, we used a time series of 23 Sentinel-2 images took in 2016. So this is an overview of the framework we propose. The JobNet framework is available online on the GitLab of our institute at this address. So what's the idea? You start from the satellite images time series. You obtain your node set by segmentation. Then you obtain your layers. You infer the membership, the node layers membership through fuzzy clustering. And then you add intra-layer and inter-layer edges in order to obtain your jellyfish here. Multilayer network. So all the complete and advanced information can be found on this paper, which has been just accepted for publication on Network Science. So extracting multilayer networks from Sentinel to satellite images time series. Okay. So here are just some definition. But we are talking about multilayer networks since some time in this session, so I won't go deep on this, but I just want to stress that here we talk about the most general definition by Kibela. So a real multi-layer network is the most general possibility of having inter-layer edges between different nodes. So it's not a multiplex, we don't have just coupling edges, but we have all the inter-layer edges you can imagine. So the problem is, just tend to go fast because the time is it's running. The problem is, given a satellite image time series, obtain a multi-layer network. It's what the title says, okay? Which is undirected and weighted. So, step one. Step one, you want to know, you want to infer your nodes. We do this by segmentation. Segmentation is a really standard process in computer vision. So you just partition your image in homogeneous segments, okay? So what's the point? In this case, to minimize the noise, we do just one segmentation for the time series, which is done on an image of the series that we call it the S star, that can be selected, for example, as the peak of the growing season, so when the heterogeneity is maximized, and when the weather is good, so there are no clouds, because the problem with optical satellite images is that if you have clouds, you are going to see nothing, okay? Which is not the case for radar ones, for example. So if you see two images of Cumbia here, you can clearly see that the image taken in August is much more clear, and there's much more vegetation diversity and heterogeneity than the other two took in April and in January, for example. So in this case, we do the segmentation on this one. So, as we said, one selected image, we partition that in a certain number of segments that will become the node set of our multi-layer network, okay? So, then, how do we infer layers? So, with fuzzy clustering, okay? First of all, what are we clustering? We are clustering the time series of NDV of each segment, okay? This is another concept which is familiar for people in remote sensing and maybe not in this room. So NDV, it's a radiometric index, okay? It's a normalized difference vegetation index. It's extremely well known and used everywhere in this domain. So it's a radiometric index computed as with the near infrared and red bands of the satellite images, with this marking. And it represents the quantity of vegetation on a certain area, on a certain pixel, okay? So we associate the time series of NDV to each pixel in the image, and then we do the average of for each segment. And then we cluster the segments based on their time series of NDV. Well, what is the point? What is the meaning of that? The meaning is that the clusters will correspond to different functional classes, okay? Because each functional class, so natural areas, cropland, urban areas, they will have different time series of NDV, completely different. So this is the meaning. So this is also helping in the fact that we can use an algorithm like CMINS, where we have the parameter of the number of clusters, okay? Because, which is important, the number of clusters in this process will become the number of layers in the network, okay? So we have a multi-layer network where the number of layers is a parameter, which can be seen as a kind of dangerous thing from one side, but it is not, because if it is easy to refer to domain expert and to the characteristic of a certain area to infer what is the supposed number of functional classes in a certain area. For example, for us it's 10, so we have, for example, 10 land cover land users in the area. So then we have the layers based on the membership probabilities. So the intra-layer edge, so the edge between the nodes in each layer will be based on the REG, which is the regional adjacency graph. So based on the adjacencies between segments. And how are these edges weighted? Are weighted based on the context of each segment. What is the context? Is how the segment is placed among other segments which have different cluster membership probabilities. So it's a way to define the context around each segment. Based on the 8 connectivity matrix of each pixel, and then the weighted sum over each segment, which comprises a certain number of pixels in their directions, okay? And then the weight is computed as the cosine distance between the context of the two segments. Interlayer edges are also added based on the regional adjacency graph, so nodes referring to segments in different layers will have an interlayer edge between them if they are adjacent in the regional adjacency graph of the image, okay? And then we propose two weighted schemes, so fixed or based on the context. So fixed, for example, half of the average weight, or based on the context, so always with the cosine distance. So I'm going to speed up, I'm going to skip the structural characteristics, they're not interesting. And just skip to some experimental result on this landscape certification task via multi-layer community detection. So this is a zoom over the Cumbia area. This is the result obtained with a supervised algorithm. So where yellow is the cropland, green is natural vegetation like forest, and blue are water bodies. We don't have any water body here, basically. So for example, if we apply a multi-layer community detection, we use an info map in this case for a series of reasons, and if somebody asks, I will answer during the question time. So this is the result for a network with 10 layers, so k equal 10 and fixed interlayer weights. We can see that the communities, we have 8 communities, but are kind of really well defined. We have the cropland in the middle, you see it was, okay, the yellow area is the cropland. The community is well placed or on the cropland or on the natural area, so we can say that this is a good result for an unsupervised algorithm. And then we have results over other parameter setting, for example, with context interlayer weights, but the best one is the first one. The others have communities which are, some communities are good, some other communities are not really well placed, are placed among the two land covers, which is not good. For example, with K2NT or on the flattened network. But this is an histogram representing the overlap of the communities on the land covers, so we don't have time to discuss this, maybe. Okay, well, just a minute to talk about the sliding window, which was in the title, but unfortunately we did not develop too much this aspect, but we have some preliminary results. So the idea of the sliding window is to have a context which describes each segment, which is richer than just looking at the immediate neighbors of each pixel. So we pass with a sliding window of a certain size, for example 100 by 100 in this case. And then we are going to calculate the cluster memberships of the pixel around this sliding window for each pixel. And so this is the result, for example. This is a clustering, this is not a fancy clustering, it's a normal k-means. And this is the result of the sliding window, which describes the context around each segment. We can see that it's interesting. For example, we have down there we have an area of natural forest which is compressed in one cluster. If we look at the context, we can see that the dark area in there belongs to a certain context, but the border, even if it is the same cluster, it has a different context, for example, because it's forest, but it's adjacent to the cropland. So it's just a richer way to describe the context of each level. So summing up, we proposed the methodology to extract a multi-layer network from a satellite image time series. We tested on this landscape stratification problem. Future challenges: investigate more understanding of context, test or develop different community detection algorithms for the case study, and integrate layers based on different semantics like interaction graphs, based on modeling, so really on the interaction with real actors on the web. And that's it. Okay.
So any questions? Start.
Yes. So first, I didn't understand, what are your layers? They are different type of vegetations or something like that?
Yeah, it's you can see them as the different classes of vegetation or different, I would say more generally functional classes, okay? Because the layers are the results of the FATSI clustering, okay? Yeah. So it's a clustering based on the NDVI time series. So it's the different functional classes. So for example, different types of vegetation, but not only vegetation. I mean, you can have urban areas and different things. So it's that, and it's a FATSI clustering because this being an unsupervised process, you can't be sure that a segment belongs to an exact class. So you will have membership probabilities on different clusters.
Sorry, just to follow up on this, I thought your layers were different time periods of the same image.
No, this can be confusing, but no. Okay. The layers are the functional classes. The time series is exploited to do the clustering and to weight the edges. Okay? Because, for example, in this context, if we talk about landscape stratification or land cover, this won't change during an year. Okay. So if an area is forest, it will be forest. Okay. If Bolsonaro is not sure that. Yes. But more or less no, just joking. But I mean the cropland. I mean the different. If there is, if in a certain crop there are cereals, for that year this is cereals. If it's pastures, it's pastures. So we can have a single segmentation for all the time series. We don't need to have a slide for each timestamp. Then you exploit the time series to do this clustering, so to infer the layers based on the vegetation profile.
I have another question. Because your images are very noisy, so you just skip on the segmentation, but all your stuff is very dependent of your first segmentation, no?
Yeah, yes and no.
Easy, the segmentation
yes and no.
is easy, or?
It's easy because the images are pre-processed to eliminate the noisy effects which come by clouds and stuff like that. So we start from images that are pre-processed, so the segmentation it's obviously a bias, okay, so that's for sure, but not so much. I mean, it's you just have to run it with the good parameters, so to have the node size that you like, okay, but it has an impact, but it's a minor one, I would say.
You mean that you can do the segmentation automatically without tuning parameters?
Yeah, this depends on the algorithm that you use. There are plenty of segmentation algorithms, so there are always parameters, but I mean, you can run it with the standard ones and obtain something that is meaningful. Because then, if your objective is to then do community detection, the impact will be minor, because even if you have a different node size, then, for example, you will have some edges with higher weights between similar segments instead of having a single node. So in the end, you will end up with the same results.
But I was thinking maybe we can have a multiplex before, using the different segmentation algorithm. You can have a multiplex and do processing on the multiplex.
I understand your point. We talked about this, but this would add a lot of noise. Because if you run a different segmentation for each time slice, then it's the problems. Each segmentation will be different, and you will add a lot of noise. This depends on the task. Maybe there are some other tasks where this is more meaningful to doing this, but in this case, this is true that it's better not to do that, because this will just add noise.
Okay, thank you.
Right. Any other question?
Yeah. Yeah, it's the multi-layer version of Infomap. Infomap, it's it was my presentation. Okay. Anyway, Infomap it's a really well-known algorithm. There is a multi-layer version of it proposed by Mario De Domenico and colleagues in 2015, I think. And it's particularly adapted to the case because it took into account edge weights, which is not always the case for multi-layer community detection algorithms. And it allows generic interlayer edges when most algorithms are more for multiplex. Then, as I said, I mean, one of the objectives is to test other algorithms or adapt existing ones to have something which is even more adapted to this kind of texture-based communities. But yes, this is multi-layer. Yeah.
Did you look at how the number of communities is changing, the number of layers?
Yeah, actually, it's not changing so much. Okay. If you look at the results, we have different solution, and you are always between 6 and 8 communities. The number of communities is not changing so much. The network, yes. For example, 10 layers, 8 communities. Always 10 layers, but different weighting, always 8 communities. 20 layers, 6 communities. Flattened network, always 6 communities. So it's always the same order of magnitude. It won't change so much. You want to obtain, I don't know, 60 communities or so.
Okay, so I think we
Okay, as I was explaining to Jacinto, the layers are obtained based on the fuzzy clustering. So you do a fuzzy clustering on the time series of NDV of each segment. So for each segment, you have this time series of NDV. This describes its vegetation profile during the year. Then you run, for example, a fuzzy means. So the clusters will represent different functional classes, so different types of vegetation, if you want. It is not. Yeah, no, we try, but it's not really the same thing, because then you use a fuzzy clustering to individuate fuzzy membership to these functional classes, and then you have also the edge weights based on the context. Yeah, it will be different. It won't just work just using the fuzzy clusters. So. The idea is to, because if you just run the clustering on the original segments, you won't obtain a good result. So the idea is to, how can I say, to enrich the representation of the textures through the network. So you want to just have a clustering based on the vegetation profile, like in the original one. But you will have all that regards the special context, which is a way to represent the texture if you want. So how the segments are placed among other segments. And so you will have edge weights based on the difference between these contexts. So it's a way to enrich the description of a spatial context of each segment. And you won't obtain that just by clustering the original NV time series.
So it's also a way to smooth and have adjacency segments, which is similar. Because I suppose that the research is coming does not
No. The clustering is based on the vegetation profile. So this has nothing to do on the spatial position on the image. It's just the vegetation profile. Exactly. I mean, you are kind of combining spatial information with radiometric one, textual one. Exactly this.
Right, so we'll move on. So thank you.